Okay, so here's something really interesting. I'm going to show you an example of what we call a fractal set, a set which has a fractional dimension. So you're used to sets like these, say a straight line, a square, and say a cube, where these sets have dimensions which I would say you would tell me and you would know. You would say that this one is one-dimensional. You would say that this one is two-dimensional. And you'd say that this one down here is three-dimensional. Why do we think of those things as one, two, and three-dimensional respectively? Well, here's an idea. Suppose the line has length 1, and I magnify it sort of by 2. So I now give it length 2. And I'm going to do the same thing to the square and to the cube. So apologies if the dimensions don't come out right. I'm just trying to fit it in the space I've got. So rather than having a 1 by 1 square, which has area 1, I've now got a 2 by 2 square, which has area 4. And similarly, for the cube, if I look at this one, and it's not going to actually be as big as it should be here, but that's 1 by 1 by 1, which is 1, and a 2 by 2 by 2 cube is 8, and so if I similarly apply a scale factor of 3 here, the line is still just 3. A 3 by 3 square has area 9, and a 3 by 3 by 3 cube would have volume 27. In a sense, I'm using volume and an area and things interchangeably. I mean, the sort of here, the two-dimensional volume is kind of an area, the one-dimensional volume is a length, and we could extend to more dimensions if we wanted to. The sort of dimension I want to try and aim at is somewhere between 1 and 2, though. So let's just really clarify what we mean by the dimension here. So it might help if I write here that 1 is equal to 1 to the 1. Not very helpful so far. 2 is equal to 2 to the 1, and 3 is equal to 3 to the 1. Similarly, here for the square, I'm going to write 1 is equal to 1 squared, and 4 is equal to 2 squared, and 9 is equal to 3 squared. Down here I've got 1 is equal to 1 cubed, 8 is equal to 2 cubed, and 27 is equal to 3 cubed. So I hope what you can see here is that between the shapes in this first column and the second, I multiply by a scale factor of 2 all of the dimensions, and from here to here we have a multiplying by a scale factor of 3 to get to the third column. And so we can see then that that scale factor here appears consistently as this number, and as this number, and then the dimension appears consistently as this number. The dimension squared, 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 cubed, cubed, cubed. So in some sense, if when I apply a scale factor of s to a shape, if that shape has dimension d, I expect its new volume to be equal to that scale factor to the power of the dimension. So, quite interesting. How can we come up with a set which has a fractional dimension? Well, here's an example of one. So, if I take a triangle, and so let me draw a triangle as best I can, and from that triangle I'm going to remove a sort of similar triangle in the middle, kind of upside down version of it, and just get rid of that area. And then from each of the triangles that remain, these 3 triangles, I'm going to remove the middle piece. Alright? And then from each of those triangles, I'm going to remove the middle triangle. I just keep going like this. And, you know, this thing is going to take me quite a while to draw because I'm going to try and repeat this process infinitely. So you'll be pleased to know that in this video, this is the last layer of triangles that I'm going to draw. And of course, all these triangles are much more perfect than I have drawn them here. But what then happens to this shape if I apply a scale factor s of 2? Well, I will show you exactly what is going to happen. So when I apply a scale factor of 2, what happens is the resulting picture looks a bit like this. I start with a triangle that is twice as big. This sort of big triangle around the edge, and I, at my first step, remove this triangle in the middle. And then from the 3 resulting triangles, I remove their middles, and go on infinitely. So there, what we have ended up with, if the thing that I started with had sort of, call it area, volume, whatever you will, 1, what I've ended up with is 1, 2, 3 copies of this initial thing. So then I've got 3 here as my V. So if this is to have some sense of dimension, then 3 must equal 2 to our dimension if it's going to be consistent with what we've done before. Now, we know that 2 to the 1 is equal to 2, and 2 to the 2 equals 4, and we want a number 2 to the d, which is equal to 3. So this number d looks like it's going to be somewhere in between the numbers 1 and 2. So, what is d if we want to be more precise? Well, if you've met the concept of a logarithm before, you will maybe say that d is the logarithm to the base 2 of the number 3, or in log 10, just log 3 over log 2. But that doesn't really matter, it's just a number between 1 and 2. I think somewhere about 1.7ish, but I'm not totally sure on the exact number, but definitely something between 1 and 2. So that's what we mean then by a fractal set. It's a set which has fractional dimension. Thank you.